Okay, this video is going to be for sections 16.1 to 16.2, the reading guide. Couldn't get my audio to work on Friday, so I'm recording this from my iPad, so that's why it looks a little bit different. But anyway, here we go. So we've talked about, pretty sure we've talked about a couple definitions of acids and bases so far, so this might be a little bit review, but I know the people who were actually in class on Friday after school didn't remember this very well, so it's probably worthwhile to go over it. There's a couple of definitions for acids and bases. One is Arrhenius, one is a Bronsted-Lowry, and the other one that is not mentioned here, but I want to just mention it again because we've talked about it a while ago and it would be good to review, is Lewis acids and bases. So Lewis acids and bases is the most general, and I guess I'll cover that after we talk about Bronsted-Lowry. So let's go back and start with the most specific, the most limited definition. And this was also the first one for acids and bases. So Arrhenius said, an acid is a substance when you dissolve it in water. It increases the concentration of hydrogen ions. All right, so a good example of an Arrhenius acid, easy example, would be HCl. Okay, so HCl, you put it into water, it splits apart into H plus and Cl minus. Okay, so that's an acid because when you put it in water, now you have more H plus in there than you did before. Okay, so that's his definition of an acid. A base is a substance when dissolved in water increases the concentration of hydroxide ions. So that could happen a couple of different ways. One way that it could happen is if you've got something like sodium hydroxide, NaOH, that dissociates in water. Now you've got Na plus and OH minus. Okay, so obviously that's increasing the OH minus concentration. But there are other things that can do that as well. One of them is NH3. Okay, so NH3, you put it into water, so you've got H2O moving around in there, and what the NH3 can do is actually steal a hydrogen from the water. So now you end up with NH4 plus, and because it took a hydrogen away from the water, now the water becomes OH minus. So this is also increasing the concentration of OH minus in the solution. All right, so those are Arrhenius acids and bases, but in order for that to work, it has to be in solution. Okay, so that's a fairly limited definition. Bronsted-Lowry came up with the definition that an acid is just a proton donor. Now, if you think about what a proton actually is, another way to say a proton is just H+, because hydrogen on the periodic table has one proton, one electron, and that's it, no neutrons. So you get rid of its one electron to make it positively charged like this, and all you've got left is a proton. So H+ and proton are basically interchangeable terms. Right, so just be aware of that. The base is a proton acceptor, so it changes the definition a little bit to say it's a proton acceptor. It may not be increasing the concentration of OH minus in the solution necessarily, but as long as it's accepting an H plus from somewhere else, then you could call it a Bronsted-Lowry base. Okay. I'm trying to think of a good example of that. I suppose. So again, you've got NH3, and you react that with hydrochloric acid, maybe HCl. Now, the way that this would work is Bronsted-Lowry doesn't limit it to being in solution, right? So it doesn't have to be, these could both be gases, right? And we would still consider this to be an acid-base reaction because what's happening here is the H plus moves to the NH3, so now you end up with NH4 plus and Cl minus. Okay, and so actually what happens there, if you put ammonia and hydrochloric acid next to one another and allow them to just sort of, we know that NH3 is very, very strong as far as its smell. HCl also, concentrated HCl will also change to a gas fairly quickly, so you can see smoke coming from it. So if you set a beaker of concentrated hydrochloric and concentrated NH3 next to one another, they will actually form this film on the outside of the beakers. And this film is actually just ammonium chloride because the NH4 plus and the Cl minus come together, form this salt that gets on the outside of the beaker. So that's an example of a Bronsted-Lowry base and acid. And again, it's a little bit broader definition than Arrhenius, because Arrhenius, it has to happen in water. Now, Lewis acids and bases are the most broad category. And I don't know if you remember this or not, but Lewis acids and bases, a Lewis acid is a proton acceptor, and a Lewis base is a proton donor. I said that wrong, sorry. Lewis acid is an electron pair acceptor. Actually, I think I said that part right. Lewis base is an electron pair donor. All right, so one of the examples we looked at with that was any of the coordination complexes or the complex ions. So an example of that might be you've got Cu2+, okay? That's your Lewis acid because it's going to accept protons. And then maybe you have something like NH3, which is your ligand. And again, you might have to look back to remember this. But a ligand is basically the electron pair donor. It's the thing that connects to the metal in the metal complexes, the coordination complexes. And so what's happening here, this NH3 is the electron pair donor. The copper is the electron pair acceptor, so we call the copper the Lewis acid. And we would call the ammonia the Lewis base. Okay? Now this is the most broad of the three definitions of acids and bases because it works for for things even if a proton is not being donated or accepted. Here we're just looking at electron pairs kind of hooking on to one another. Okay? And so what you would end up forming from that is a coordination complex, maybe like CuNH3,4 perhaps, and that would be a 2+. So I don't know if you remember these or not, but hopefully that comes back to you. But that's the Lewis acid base thing. We're going to kind of drop that definition for the rest of the chapter, but I wanted to remind you of it because I think you might see it on the AP exam in the context of the coordination complexes. Okay, so for a Bronsted-Lowry acid to be an acid, it must have a removable proton. In other words, a removable H. That can become H plus and bond to something else. Bronsted-Lowry base must have a pair of non-bonding electrons that H plus can attach itself to. All right? So that's kind of the idea. Now again, remember Bronsted-Lowry base NH3 fits that definition because it has a pair of non-bonding electrons. The H plus can just hook onto it, and you have NH4 plus. Okay. And there are some things that can be either Bronsted-Lowry acid or Bronsted-Lowry base if they're amphiprotic. Okay, that's probably a good term to know. It means that something can act as an acid or a base depending on the situation. So HCO3 minus is an example of that. You could maybe think of a scenario where an H plus comes in, combines with this, and it becomes H2CO3. Okay, so in that sense, in that situation, it could be a base. You could also think of a scenario maybe where the H that's over here on the side actually leaves on the left side, and then you end up with CO3 2- carbonate ion. Okay, so either one of those can happen, so it's amphiprotic. Same thing with HSO4-, could be H2SO4, or it could be SO4 2-, depending on whether it gains another hydrogen or that one leaves. Now the one that might surprise you a little bit is water. Okay, water can act like an acid or a base depending on the situation. If it gains an H plus, then it becomes H3O plus, which is called hydronium. Okay, now this might look a little familiar because a few labs back I think we had some confusion about what H plus and H3O plus were. H plus and H3O plus, we're going to kind of use them interchangeably in this unit, but H3O plus is probably the more correct way to write what's going on with an acid, because with an acid it's giving away H pluses, in solution at least. That H plus is going to immediately connect to an H2O molecule, a water molecule, and form H3O plus. Okay, and it forms in a 1-to-1 ratio, so the concentration of H plus in the solution is always going to be equal to the concentration of H3O plus in the solution. But there's another scenario where water can lose a hydrogen, and if it does that, it becomes OH minus. So in that sense, it could act like an acid. Okay. I may have said that backwards before. If it's gaining a hydrogen in H+, it's going to act like a base and form H3O+. If it loses a hydrogen, then it's acting like an acid, and it's becoming OH-. Okay? Alright, so what happens when an acid dissolves in water? Here's just kind of a particulate diagram of what's going on here. So you've got the HCl colliding with the H2O, and what ends up happening is that hydrogen sticks to the oxygen. You've got two lone pairs here, right? So it's fairly easy for that hydrogen to be attracted to the oxygen, and then you end up with H3O+ and a Cl-. Okay? So in this case, the water is acting as a base because it's accepting a hydrogen or accepting a proton. Bronsted-Lowry base specifically. And then they're talking about this thing called a conjugate base. So we need to talk a little bit more about that. Okay, conjugate comes from the Latin word conjugare, or conjugare, I'm not sure how you say that, meaning to join together. Reactions between acids and bases always give their conjugate bases and acids. So this is a little confusing. Students have trouble with this. We're going to practice it tomorrow. But the way this works, so on the left side of the equation, those are the ones that are usually labeled as acid or base. Okay, and then the ones on the right side are usually labeled as conjugate base, conjugate acid. That's kind of the way that it's normally done. But if you notice here, the reason that HNO2 is acting like an acid is because it's giving away a hydrogen to the water. So this hydrogen is basically going over here. Okay, so then you end up with NO2-. Alright, and then same thing, the H2O is acting like a base here because it's accepting the H+ and becoming H3O+. Alright, so that you've got your acid and your base. But the thing is, this is an equilibrium. Every acid-base reaction is an equilibrium. I say every acid-base. Strong acid, strong base reactions we don't usually count as being an equilibrium. So maybe that's not the exact correct thing to say. But you can consider most acid-base reactions as equilibrium reactions. Okay, so you've got this HNO2 that's becoming NO2-, but if you think, so normally we think about a reaction happening in this direction, right? But you can also, because this is equilibrium, it's reversible, which means we can think about it happening in this direction where it goes from the right to the left. So if that's the case, then when it's going from right to left, this H3O+ is giving a hydrogen to the NO2- and forming HNO2 and H2O again. Now in this case, because the H3O+ is giving away a hydrogen, it's the conjugate acid. Okay, and the NO2- is accepting a hydrogen, it's the conjugate base. Alright? So this acid is connected to this conjugate base. That's why they give them the same color, because on one side it's an acid because it's giving away a hydrogen. On the other side, that species is a base because it's accepting one. Okay, same thing with the base and the conjugate acid. They gave those the same color because on one side it's a base accepting a hydrogen. On the other side it's an acid, conjugate acid, giving away a hydrogen. Alright? So again, hopefully that makes sense. We're going to do some practice with that in class, so it should after we practice it. So strong acids, we've already talked about this earlier in the year. I don't know if you remember it. Strong acids completely dissociate in water. And their conjugate bases will be fairly weak. Okay? So the general rule here is the stronger the acid, the weaker the conjugate base. And the stronger the base, the weaker the conjugate acid. Okay? So an example of that would be like HCl in water. Okay? So HCl plus H2O. HCl is one of the strong acids. Now how do you know that's a strong acid? Because it's one of the 7 you're supposed to memorize. I don't know if you remember that or not. And they actually didn't put all 7 on this list, so this isn't comprehensive. But you might want to go back and take a look at those. And see if you can remember which ones are the strong acids. You're going to need to know those 7. Okay, HCl is obviously one of those. We talk about it a lot, being a strong acid. Because it completely dissociates in water, it usually doesn't go back the other direction, so we usually write that as a forward arrow. So this hydrogen is going to give away, now this HCl is going to give away hydrogen to the water. Okay, so in this case, here's your acid, here's your base, On the other side, you end up with Cl minus and H3O plus. Okay, so this is your conjugate acid. I'm just going to label it Ca because I don't have room. And this will be conjugate base. Okay, so HCl is a strong acid, right? Because it dissociates completely in water. What that means is the H and the Cl don't really want to go back together in water. Okay, so saying that this would happen where the H3O plus gives away a hydrogen to the Cl minus so that it becomes HCl again, that just usually isn't going to happen because the HCl likes to stay dissociated. That's the definition of a strong acid. Okay, so that basically means that this reaction really doesn't go back this direction. So we write it as just a forward arrow, okay, not an equilibrium reaction, and that's the way that strong acid reactions usually work. Strong base reactions are the same way. Okay, so notice your acid is very strong, so your conjugate base is very weak. In other words, it doesn't like to accept a hydrogen, so we call it a weak conjugate base. Okay, so you can look at this chart here, and you can see, go down to the very bottom. CH4 is negligible as far as its acid strength. That carbon doesn't like to give away any of those hydrogens, okay? And we'll talk about why later. We'll hit that towards the end of this chapter. But it doesn't like to give away a hydrogen, so it's a fairly weak acid, a really weak acid, actually. But if you have CH3 minus in a solution, that's a very strong base, okay? Because CH3 minus, not very stable. If it gets an H plus from somewhere, then it will become CH4, which is stable. Okay, and so then you've got a situation where the CH3 minus is a really strong base because it'll grab H pluses from pretty much anywhere that it can get them to turn into CH4. But CH4 is not very eager to turn back into CH3 minus, so it's a very weak acid. So hopefully that makes sense. Substances with negligible acidity do not dissociate in water. Okay, that means their conjugate bases are extremely strong. So that's the example we were just talking about here. CH4 to CH3 minus just doesn't happen. CH4 stays together in water, so we would call it, to use our terminology that we used earlier in the year, strong electrolyte, weak electrolyte, non-electrolyte. I don't know if you remember that or not. NaCl is an example of a strong electrolyte because it completely dissociates in water. You end up with Na plus, Cl minus. Example of a weak electrolyte might be like something right in the middle here, like acetic acid, HC2H3O2. Okay, it's going to partially dissociate, but most of it doesn't. So every once in a while, it'll lose one of these hydrogens off of here. So it will increase the H plus concentration in the solution a little bit, but that's considered a weak electrolyte because it doesn't happen all that often. Now CH4 would be considered a non-electrolyte because it doesn't break apart in water. It just doesn't. So hopefully you remember all that. Let me erase some of this so you can see the rest of the writing on this screen. Oh, there isn't any more. Figures. Okay. So in any acid-base reaction, equilibrium is going to favor the reaction that moves the proton to the stronger base. Okay? I'm not sure if that's the easiest way to think about it necessarily. I think what works for me is just thinking about which one of these reactions is more likely to happen, the forward or the reverse reaction. So you've got, HCl is a strong acid, so for it to give away a hydrogen and form H3O plus and Cl minus, pretty likely, right? To go back the other direction so that the H3O plus gives a hydrogen back to Cl minus and it forms HCl, not all that likely. Okay, so the equilibrium lies heavily to the right on this one, which means that we would have a big, big K. All right, in fact, so big that K really isn't even measured. So that's why we don't talk about these strong acid base reactions being equilibrium reactions, because the K is just so enormous. It's impractical to work with. Okay? But then you've got something like this, okay? Acetic acid reacting with water to form H3O plus and CH3CO2 minus, which is acetate. the acetate ion. So if you look back at the chart here, acetate is C2H3O2 minus. That is a stronger base than water, okay? Because water up here, now we're sort of in the negligible end of things, okay? So as you go down, the base strength is increasing. So C2H3O2 minus is a stronger base than water, okay? Now you could also look at the acid here. I don't know, it doesn't have to be the base. So H3O plus versus acetic acid. If you look at those two, notice that H3O plus is higher on the acid strength scale than the acetic acid. Okay, so what that tells me is it's going to be, based on that chart, it's more likely that the strong base and the strong acid are going to react, and the strong base and strong acid are both on the right side on this one. Okay, so it's likely that this H plus is going to give, or this H3O plus is going to give a hydrogen to the CH3CO2 minus, and it's going to push the equilibrium back this direction. Okay, it's less likely, because this is your weaker acid and base on the left side, less likely that that this is going to give away a hydrogen and form what's on the right side. Okay, so you can say that the equilibrium favors the left side on this one because it's going to tend to move in that direction. So you're going to have and by favors the left side, all that means is you're going to have a greater amount of the reactants in this particular equilibrium than you do of the products. Okay, because the products like to turn to the reactants more than the reactants like to turn to the products. Hopefully that makes sense. Another way you can write this, and I don't usually do this, but if you want to show the relative sizes of the equilibriums, oops, I did that wrong. You can actually say, okay, so this one's a shorter arrow, this one's a longer arrow, and that basically shows that the equilibrium lies more towards the left side. If you want to do that, that's fine. Sometimes you might see that kind of notation. I usually just stick with the normal double arrows here. Okay? Alright, I think that's pretty much it, so we'll see you in class.